Myself, I. Ratnamala, Assistant Professor of Physics, V.V. Vani Perumal College for Women, Virudhunagar. In this module, let me explain the basics of statistical mechanics, hence ensembles. All we know that what is statistical mechanics? Yes, it is the branch of physics which includes the principles and procedures of statistics, which combines the laws of both classical as well as quantum mechanics, particularly with respect to a field of thermodynamics. Moreover, it describes how the macroscopic observations like pressure, temperature and volume are related to the microscopic parameters. It also uses the probability theory to determine the distribution of molecular motions and particles states within the system. For example, the particles occupy the system which consists of so many energy levels. Each energy level could have several energy states. The particle occupies the particular energy states and it particularly depends upon the energy of the respective particle. Let me explain the kinds of particles. Particles which are regulated by Maxwell-Boltzmann statistics have to be distinguishable with each other. So therefore, one energy state could be occupied by two or more particles. Here, the term distinguishable means, let us consider two particles. Let it is named as A and B. Also, we consider two states, that is named as 1 and 2. And if we put the particle A into the state 1 as well as the particle B into the state 2. So therefore, it will be different with the distribution of A to state 2 and the particle B to state 1. So it means that the particles A and B are distinct with each other. Such type of statistics is referred to as Maxwell-Boltzmann statistics. Next comes Bose-Einstein statistics. Here the particles are indistinguishable with each other. Also, one energy state can be occupied by two or more particles. So, instead of saying that the particle A and B, we could just call it as a particle. So, since they are the same thing in the case of Bose-Einstein statistics. Next comes Fermi-Dirac statistics. Here also the particles are indistinguishable with each other, but here one energy state could be occupied by only one particle. So we have to fill the another state when the state just has been occupied by another particle. So in the case of Maxwell-Boltzmann statistics, molecules of a gas is the best example because here the particles are identical and distinguishable with each other. Moreover, the particles having any type of spin is applicable to this kind. Next comes quantum statistics. Among this, the first one is Bose-Einstein. Bose-Einstein particles are applicable to identical and indistinguishable case. Here the particles having either zero spin or integral spin. Such particles are referred to as bosons. Examples: photons, helium atom, etc. And the third kind is that Fermi-Dirac statistics. Here the particle is applicable to identical and indistinguishable one. Here the particles having half integral spin and they are referred to as fermions. So such type of particles obey Pauli's exclusion principle. The best example of this kind is electron, proton, etc. So among the three statistics, the first one, Maxwell-Boltzmann statistics, is also referred to as classical statistics, and the other two kinds, that is Bose-Einstein and Fermi-Dirac, comes under quantum statistics. Here comes the difference between the two particles. Yes, bosons and fermions. Bosons are the particles having either zero or integral spin. It doesn't obey Pauli's exclusion principle, and here it obeys symmetric wave functions. So any number of bosons can exist in the same quantum state, but whereas in the case of fermions, such different, yes, here the particles having only odd half integral spin, and it also obeys Pauli's exclusion principle, and here it represents antisymmetric wave functions. Here only one fermion can occupy the particular quantum state of the system. Next comes ensembles. First of all, we consider the system. The system is nothing but a collection of large number of particles, hence define ensemble. It is nothing but a collection of large number of independent systems. Moreover, it satisfies the macroscopic conditions like volume, energy, pressure, and the total number of particles inside the system, etc. Here, the term independent means it mutually non-interact with each other. Therefore, it differs in its microscopic parameters like parity, symmetry, quantum states, energy level, etc. Next comes the types of ensembles. Ensembles broadly classified into three types. The first one is microcanonical ensemble, canonical ensemble, and the final one is grand canonical ensemble. Here is the pictorial representation of the three kinds of ensemble. Let me explain one by one. First comes microcanonical ensemble. It is a collection of large number of independent systems having same energy, volume, and total number of particles. Here energy is represented by the letter E, and volume is by the letter V, and the total number of particles by the letter N. In the case of microcanonical ensemble, the systems are separated by rigid impermeable as well as insulator walls. So therefore, the values of energy, volume, and total number of particles are not affected by the presence of mutual pressure of the other systems. Here comes the pictorial representation of microcanonical ensemble. Here we see that it is the impermeable wall, and here all the ensemble members having same value of energy, volume, and total number of particles. So therefore, here there is no transfer of energy and mass takes place within the system. No transfer of energy takes place. Moreover, here the ensembles are isolated one. Here is the another pictorial representation of microcanonical ensemble. Here the ensembles having same volume, energy, and number of particles. Next comes canonical ensemble. It is a collection of independent assemblies having same temperature, volume, and number of particles. Here it is the ensembles are separated by rigid, impermeable, but thermodynamic diathermic walls. Diathermic walls is nothing but conducting walls. So here the equality of temperature is attained in order to bring the system in thermal contact with each other, because here the walls are separated by rigid, impermeable, and conducting walls. So therefore it allows heat to flow through them, but do not allow the exchange of mass within the ensembles. So here energy can be exchanged between the assemblies and reach the common temperature. This kind of ensemble is best suited for isolated system. Here is the pictorial representation for canonical ensemble. Here we see that it is the large reservoir having constant temperature. This constant temperature is attained with the help of diathermic walls, and all the ensembles members having same value of volume, temperature, and number of particles. So So therefore here energy can be exchanged, but the number of particles can't. So here is the another representation for canonical ensemble. Here the walls are nothing but diathermic one. Next comes grand canonical ensemble. Grand canonical ensemble exchange both energy as well as the number of particles within the reservoir. It is the collection of large number of independent system and it attains same temperature, volume and chemical potential. The chemical potential is represented by the letter mu. The individual assembly system of a grand canonical are separated by rigid permeable and conducting walls. So therefore here exchange of energy as well as the number of particles takes place. So therefore it attains the common chemical potential within the system. Here is the pictorial representation for grand canonical ensemble, and it is the large reservoir having temperature, constant temperature T, and all the ensemble members having same volume, temperature and chemical potentials. Here both the energy as well as particles can be exchanged within the system, and here we see that it is a permeable as well as diathermic walls. And finally the comparison between three kinds of ensembles. In the case of microcanonical ensemble, we see that U, V and N having same value, but here the temperature fluctuates, whereas in the case of canonical ensemble, temperature, volume and number of particles having same, but U fluctuates. Having constant temperature is attained with the help of diathermic walls, whereas in the case of grand canonical ensemble, the system having same temperature, volume and chemical potential, but here both energy and mass changed. So therefore N and U fluctuates within the system. I hope all you get some idea behind the basics of statistical mechanics as well as ensembles. Thank you.